Hey, hello guys, welcome to the another lecture series on electric charges and electric field. In the previous video, we discussed about torque experienced by an electric dipole in an electrical field and also the potential energy of electric dipole in an electrical field, external electrical field, alright. So today in this video, we're going to take a small problem on this torque and also the potential energy, and let's try to understand what exactly is the potential energy. Alright, so let's get started. So we're going to discuss sample problems today. Okay. All right, sample problems. First, we will discuss about torque, and then we will gradually get into potential energy also, right? So the first question is something like this: two equal charges, say 2 microcoulomb and minus 2 microcoulomb, are separated by a distance, say separated by distance 2 millimeter. Okay. Now the questions are like this. First sub question is find the dipole moment. Find the dipole moment. Okay, that's your first question. And the second question is, if this dipole is placed in an electric field of say 20 Newton per Coulomb in an electrical field of little more, we will take say 200 kilonewton per Coulomb, then what is the net force? What is the net force experienced by dipole? That is one of the question. And the other question can be like this: if the dipole is at an angle of 30 degree, then how much is the torque? How much is the torque experienced by dipole? All right. And the other question that we can include in it is, if the dipole is further rotated by 30 degree more, then how much work is required? How much work is done? Okay, how much work is done? Okay, see, one question they can ask many things in that, right? Just only one statement. They've just given that two equal and opposite charges, or the two charges are separated by so and so distance. Magnitude of the charge is given, the separation between two charges is also given. Okay, so using that information, what can we find out? The dipole moment. That is the first question, right? So how do I find out dipole moment of a dipole? Let's get into the solution. Okay, so here, for the first sub question, the dipole moment is written as P, which is Q into 2A, right? So Q is what? Magnitude of any one of the charge. I have two charges here, 2 microcoulomb, and another charge here, minus 2 microcoulomb. And these two are separated by what distance? They have given that as 2 millimeter. All right. Now Q is 2 into 10 to the power of minus 6 Coulomb. Why am I writing like this? It's micro, no? Micro is how much? 10 power minus 6. You should remember that centi. Let me write that here. Centi is 10 power minus 2. Milli is 10 power minus 3. Micro is how much? 10 power minus 6. Nano is 10 power minus 9. Okay. Then you will also have something called pico, which is 10 power minus 12. You should remember all these things. Okay. And then you have 10 power 3 as kilo, 10 power 6 is mega, 10 power 9 is giga. All these things will be there. So you have to remember all these things are very important. Now here they have given it is 2 micro coulomb, right? So micro is 10 power minus 6, then coulomb. And then the 2a itself is what? Distance between two charges, right? And how much is that? They have given it as 2 millimeter. So I have to convert that into meter. So milli is how much? 10 power minus 3. So it is 2 into 10 to the power of minus 3 meters. So I have got Q, I have got 2a. So that's all I wanted. So what is going to be my dipole moment then? Q is 2 into 10 to the power of minus 6. 2a itself is 2 into 10 to the power of minus 3. Your unit is going to be coulomb meter. It's not centimeter, it is coulomb meter. Okay, be careful. And some people will take a as a distance between two charges. They don't ever make that mistake. 2a itself is a distance between two charges. Okay, 2a itself is the distance between two charges. All right. So now if you do the simplification, the calculation, you're going to get 2 into 2 is 4. 4 into 10 to the power of minus 6, 10 power minus 6 into 10 power minus 3 is 10 power minus 9 coulomb meter. And that is your dipole moment. That's the answer for the first question, right? Easy, right? Now the second question is what? If this dipole is placed in an electrical field of 200 kilonewton per coulomb, the electrical field strength is 200 kilonewton per coulomb, it seems. Okay. Then what is the net force experienced by this dipole? Let's draw the electrical field here. Okay. So let us draw the electrical field. Okay. So I have this electrical field here. Let's draw a few more electrical field lines. All right. Now in this electrical field, I'm going to keep a dipole. Let's say I have kept a dipole like this. No matter how you keep, somehow in any orientation, they have not told in which orientation you need to find the net force. In fact, in any orientation, the net force will remain the same. Net force, I'm not talking about torque, I'm talking about net force. Okay? I'll explain that why in any orientation the net force will be same. You will see that now. I have an electrical field E, uniform electrical field. In that uniform electrical field E, if I keep a charge Q, how much will the force the charge Q will experience? How much force will the charge Q experience? It is E into Q. You all know that. In the previous video also I've explained that. If you haven't watched that, please go and watch those videos so that you will have proper understanding of why this charge will experience a force of E into Q. All right. So now, this is that EQ is the force experienced by this positive charge, and that will be in the direction of electrical field. And this negative charge will experience a force in the opposite direction of electrical field. How much will be that? That will also be EQ only. So now you see there are two forces. One force is EQ to the right, and the other force again EQ in the left. So the net force will be 0, right? They are in equal in magnitude and opposite in direction. So the net force will become 0. Now no matter whatever is the orientation, net force will always be 0. Net force is always 0. That does not mean that the torque is 0. Okay? The dipole will still rotate, but it will not move anywhere. Net force 0 means what? The dipole will not move anywhere. In its own position, it may rotate. That rotation is because of torque. And the movement is because of force. But here force is 0, no? Net force is 0, right? Therefore, the dipole will not move anywhere. But in its own position, it will start rotate. It may rotate depending on whether the theta is 0 or some other angle. Okay? So in this case, I have just taken theta to be some angle. Okay? It may be whatever it is. So in this case, according to this diagram, the dipole is experiencing a torque, but net force is 0. So net force, I'll write it as a note. Net force experienced by a dipole in a uniform electrical field is always 0. Okay? Net force experienced by dipole in uniform electric field is always 0. Remember that. Okay? Uniform electrical field. In non-uniform electrical field, yes, dipole will experience force. Okay? In uniform electrical field, it will not experience any force. Why I am saying that in non-uniform electric field, it will experience a force? See, the name itself indicates non-uniform. Non-uniform means what? In this region, the electrical field will be different. Here, the electrical field will be different. Here, the electrical field will be different. Then this EQ and this EQ will not be equal, no? Then the net force will not be zero, right? So that's the reason. So now, let's move to the third sub-question. The third sub-question says that, if the dipole is at an angle of 30 degree, then how much is the torque experienced by the dipole? Suppose in the same diagram, let's say this angle is 30 degree. Okay? Let's say this angle is 30 degree. Then how much is the torque? Now we know the formula for torque, right? So what is the formula for torque? It is P vector cross E vector in vector form. And when you expand that, and get the magnitude, or when you write the magnitude, it is just going to be PE sine theta. Easy to remember. P vector cross E vector, which is nothing but PE sine theta, is the magnitude. Now the dipole moment is already known to us. We just found that here, right? The dipole moment is already known to us, which is 4 into 10 to the power of minus 9. So 4 into 10 to the power of minus 9 into electrical field. How much is the electrical field? They have given that. How much is that? 200 kilonewton per coulomb. Okay? 200 kilonewton. Kilo means how much? 10 power plus 3. Kilo is how much? 10 power plus 3, right? So 200 kilo, 10 power plus 3 I have written there. So 200 into 10 power 3 Newton per coulomb, Newton per coulomb. If I had said it as Newton per meter, I'm sorry that. It's not Newton per meter, obviously it's Newton per coulomb, all right? And then sine of angle between the dipole moment. Dipole moment is from minus q to plus q. Dipole moment direction is from minus q to plus q, and the electrical field is to the right. So the angle between dipole moment and the electrical field is 30 degrees. So sine 30. Sine 30 is how much? 1 by 2, right? So that 1 by 2, sine 30 is 1 by 2. 1 by 2 will get cancelled with this 2 here, so you will just get 100 here, right? 100 into 10 power 3 is going to be how much? 10 power 5, right? 10 power 5 into 10 to the power of minus 4 is going to be how much? 10 power 5 into 10 to the power of minus 9 is going to be 4 into 10 to the power of minus 4. All right. So that is your torque. Newton meter is the unit. Force into perpendicular distance, right? Torque. So the unit is Newton meter. All right. So we got to know the torque. Torque is 4 into 10 to the power of minus 4 Newton meter, it seems. Okay. All right. So because of this torque, this dipole will start rotating. Now if you look at the above diagram, it will rotate in the clockwise direction. It will obviously rotate in the clockwise direction. Okay. Because this charge, positive charge, is experiencing force to the right, negative charge is experiencing force to the left. All right. Now the fifth sub-question D. Sub-question D, they're asking, if dipole is further rotated by 30 degree more, then how much is the work done? It is not who much, it is, I'm sorry, it is how much is the work done. Okay, how much work is done. Okay, that's question mark here. All right, now already I have this dipole. Okay, already I have this dipole at an angle of 30 degree. Further, we have to rotate it by 30 more degree. Okay, that means finally the dipole will be at an angle of 60 degree with respect to external electrical field. All right. So I have this electrical field which is 200 into 10 power 3 Newton per coulomb, and I have this dipole now initially at an angle of 30 degree, plus q here, minus q here, initially at an angle of 30 degree. Now we are going to rotate it further by 30 degree. That means finally the dipole will be making an angle of 60 degree. Okay, I'll just pull it little to the right. Yeah. So now this is plus q here again, minus q. Now further we rotate it by 30 degrees, so overall it is at 60 degree. Okay, so this is my initial position, initial orientation. That is my initial orientation, and this is my final orientation. I have rotated it, okay, from 30 degree. It was initially at an angle of 30 degree. Further, I rotate by 30 degree more. Therefore, overall angle will be 60 degree with respect to electrical field. Okay, don't get confused. Easy only. Okay, so now how much extra work that we did to rotate it from 30 degree orientation to 60 degree orientation. Okay, 30 degrees initially like this. Okay, further we rotated by 30 more degree. That means 60 degree with respect to external electrical field, 60 degree overall. So how much work we did is the question. So all that you have to do is you have to find out final potential energy at 60 degree minus initial potential energy at 30 degree. So work done in this case is going to be work done is equals to final potential energy minus initial potential energy, as simple as that. Okay, now what is the formula for potential energy? Potential energy of a electric dipole in an electrical field is given by minus p vector dot e vector minus p vector dot e vector, which is pe cos theta. When you expand that, you will get pe cos theta as the potential energy formula. So we are going to substitute that here, minus pe cos theta final minus pe cos theta initial. Okay, be careful here. This minus I have written as it is here, and the initial potential energy is minus pe theta initial. Okay, now from this you can take pe common, right? In both the terms you have pe common. So if you take that, here it is minus into minus will become plus. So you will get theta initial minus theta cos theta final. All right. Now I already know the value of PE, I believe. No, I don't know the value of PE, but I know P and E. PE is how much? We calculated it here, 4 into 10 to the power of minus 9. So I'll write PE is 4 into 10 to the power of minus 9. How much is the electrical field? 200 into 10 power 3. They've given that, right? 200 kilonewton per coulomb. Into cos theta initial. How much is the theta initial? 30 degree. How much is the theta final with respect to electrical field? 60 degree. Okay. And now you simplify this. How much do we get here? 4 2s are 8. 8 into 10 to the power of minus 4 it will be, right? Because this 200 can be written as 2 into 100. And the 100 into 10 power 3 is 10 power 5. 10 power 5 into 10 to the power of minus 9 is 10 power minus 4. Okay. And this 2 into 4 is 8. Remaining cos 30. Cos 30 is how much? Root 3 by 2. Minus cos 60 is how much? 1 by 2. Alright. So what do we get? Our final answer is root 3 minus 1, okay, divided by 2 into 8 into 10 to the power of minus 4 joules. It is work done, right? Works unit is what? Joules, right? I have kept everything in standard unit. My final answer also will be in standard unit of work, which is joules. Okay. And now how do I get the value of this? This is 2 1s are 2, 4s are 8, and root 3 is 1.7. Okay, 1.73 you can take 1.73 minus 1, which is 0.73, right? 0.73 into 10 to the power of 0.73 into 4 into 10 to the power of minus 4, okay, into 4 joules. So how much do we get? 0.73 into 4 into 10 to the power of minus 4 joules, okay. And if you simplify this, you will get 2.92, that is 0.73 into 4 will become 2.92 into 10 to the power of minus 4 joules. Okay? So that is your work done to rotate the dipole from 30 degree orientation to further 30 degree, that is total 60 degree. From 30 degree to 60 degree, to rotate the dipole from 30 degree to 60 degree, the extra energy that you have to do, or the work that you have done, is 2.92 into 10 to the power of minus 4 joules. It might be very small because the given data are like that, but in reality, this for a dipole, this itself is a huge work, because in a material, if you consider a material, it will have many dipoles. Okay? So overall work done will be more. But anyway, for this problem, this is our answer. Okay? So like this, the questions will be asked. Okay? So very simple questions, not complicated and all. You will find the similar questions even in your NCERT book. So I have given my own data in NCERT book. There will be some other data. Okay? But questions will be like this. Okay? So if you practice these kind of questions, it will be really helpful for your board. And for competitive exams, question may come on potential energy, but on torque, generally they don't ask many questions. But on potential energy, they will ask how much energy, how much work is done to rotate it from this angle to that angle. All those kind of questions can be asked. Okay, so one homework question that I will give you is how much work is done to rotate a dipole from 0 angle to 180 degree. So you can find the answer for that homework problem. Okay, how much work is done? How much work has to be done? Has to be done to rotate the dipole of moment P in an electrical field E from an angle theta equal to 0 to theta equal to 180 degree. Okay, so that is your question. So you can find the answer for this. It's a simple question. Okay, and leave the answer in the comment box. All right, fine. So that's all for this video. So we will continue in the next video. So in the next video, we're going to discuss about electric flux, which is a very important topic, and Gauss law on electric flux. All right. So till then, stay tuned. Have a happy learning. Thank you all. Bye.